We proceed with our analysis of the basis pursuit, aiming to show that solving P1 may lead to the P0 solution. And here is what we have done so far. We have defined the set CE as containing all the vectors E that lead to basis pursuit failure. If X is the original sparse solution of the system AX equals B, a vector E in this set defines a candidate solution, X plus E, that an L1 solver would prefer. Our goal is to show that this set is empty under some conditions. In order to enable such a claim, our strategy was to inflate this set while simplifying it, and then claim that its bigger version is empty. Our inflation attacked two conditions, turning them into much more comfortable inequalities, in which A, B, and even X are no longer involved. At this point, the set CS is the one we are supposed to analyze. Notice that if a vector E is included in it, then so is alpha E for any alpha different from 0. This implies that CS is a scale-invariant set. We can simplify our analysis by considering only the vectors in the intersection of CS with the unit L1 sphere, by adding the condition L1 norm of E equals 1. If CS is empty, this intersection remains empty. If CS is not empty, then the new set is not empty as well. Adding the unit L1 requirement, we simplify the two conditions and get this alternative set Cn. Again, we stress that Cn carries all there is to know about the tendency of basis pursuit to fail. If it is empty, basis pursuit necessarily succeeds. Let's look closely at Cn. Starting with the third condition, it states that the vector E should concentrate its energy on the on-support element. The second condition states that every entry in E cannot be bigger than mu over 1 plus mu. Therefore, let's put as much energy as possible in the first S terms, choosing them to be their maximal possible values, and let's see what should be required on S in order to violate the third condition. This is the resulting inequality, and with a little bit of algebra, we get to this requirement on S. If it is smaller than 1/2 of 1 plus 1 over mu, then Cn is necessarily empty. In this case, basis pursuit is guaranteed to lead to the sparsest solution. We summarize this result as a theorem, which states that if S is small enough, then basis pursuit is successful in recovering the sparse solution. Does this theorem look familiar? It should, because it is the very same theorem that claimed success for OMP. Indeed, the bound we got for success is the very same one we found for the OMP. What does this mean? Is it saying that the two algorithms perform the very same way? Definitely not. We have already seen experiments in which the two depart in the quality of treatment they provide. All that these theoretical results state is that up to 1/2 of 1 plus 1 over mu, the two algorithms are guaranteed to perform perfectly well. Beyond this bound, the two may behave very differently. One last word is in order. Let's return to the experiments we presented earlier on the OMP and the basis pursuit, and explore the relation between the actual behavior and these equivalence bounds. We see that OMP and basis pursuit lead to a perfect recovery of the sparse solution for S smaller than 8. What does theory has to say about this? Well, the mutual coherence in this specific experiment was 0.48, implying that the theory predicts success for S smaller than 1.5. So, as we can see, our theoretical bounds for success are very pessimistic and does not truly capture the performance of OMP or basis pursuit. This comes back to our discussion about all these analyses being a worst case analysis. Still, it is nothing short of amazing that we are able to claim theoretical success in the first place, even if it is of limited scope.